In this video, we're going to take a look at another technique of calculating volume when we're revolving around an axis. And this technique is called the shell method, or finding volume by shells. So imagine we have some region, some area here that we want to revolve around the y-axis. Now this area is bound by this curve here of y equals x squared minus x cubed, and we want to revolve it around the y-axis. Now right away we should be able to see that, in doing that, with our current technique of using the disk and washer method, we would have to split this function into two different functions of y and call this some function of y here and this some function of y, so that we could then subtract them. And that's a little tedious, and no one really wants to do that. It's doable, but no one really wants to. And it's really easy to just keep this as a function of x and find these little rectangles here and then try to rotate those around the axis. Well, when we do that, if we have, say, this region here, which is a little simpler than the one I just showed, if we have this region here that is rotated around the y-axis, we get the volume as pictured to the right, and it produces this solid. Well, let's take a tiny little strip, like we said here, some tiny little strip, and revolve that and see what shape does it give us. Well, that shape there is a cylinder. Okay, and that cylinder has a width of delta x, which we know using all of our integration techniques that delta x is going to approach 0, which we then say turns it into a differential dx. And so this tiny little shell of a cylinder, we can cut open and roll out to say that, really, that's just a rectangular prism where we want length times width times height. Well, what is the width here? Well, we know the width is delta x. What is our height? Well, that's determined by the function. All right, how high is this on our graph? Well, that's this point right here, and that is bound by the curve y equals f of x. And so we have that height, which is the function. We have the width, which is our delta x, which will turn to dx. And what's the length here? Well, this length is the circumference of the circle that we rotated. So that's 2 times pi times the radius. What's the radius? That's our x value. To show that on the picture, well, the radius is the distance from the axis of rotation that we're rotating around here. Well, what is that? That's our x value on the x-axis. So that gives us a volume of 2 pi x times the function dx. And if we add up an infinite amount of those, that can give us all of those cylindrical shells, which then turns us into this integral. The infinite sum gives us the integral from a to b of 2 pi x f of x dx. So that gives us a formula from which we can operate. And this formula can work for any type of function, or maybe even the difference of two functions. If we have this region R here that is bound by f of x and g of x from a to b, we can look at, well, what's the height of this cylindrical shell? Well, the height is just going to be the difference of f of x and g of x. The radius is still that x value. That's our x value here. And the width is still that delta x that approaches dx. All right, really, when delta x approaches 0, this becomes our differential dx. So we end up getting this 2 pi x times the quantity of our f of x minus g of x. So that gives us our formula here for the shell method. So the disk and washer method, we had that f of x squared and g of x squared, the difference of that times pi. Well, this is similar. Instead of looking at the cross-sectional area of a circle, we're looking at calculating the volume of a cylindrical shell. That's why it's called the shell method. And so we have this 2 pi x out front, and then the difference of the two functions. So let's look at an example. Let's say we have our f of x as sine of x squared. Now keep in mind, this is the sine of the x squared inside of the sine. Okay, it's not the sine squared of x. And we want to look at the region from 0 to radical pi over 2. And that's our interval of integration. We're going to rotate this about the y-axis. So let's look at what this shape looks like when we revolve it around the x-axis. We get this solid here. And so looking at this right away, it's very difficult to try to rewrite this in terms of the disk and washer method, because we're really only bound by this function right here. And so it's really easy to leave this as a function of x. So if we want to leave it as a function of x and rotate around a vertical axis, then that's where the shell method comes into play here, and it makes it a lot easier for us because we're set up to use that. And that we have our radius as x, we have the function as our height, and dx as our width there, and so we can integrate that. So let's set up the integral here. We would want to integrate this from 0 to the square root of pi over 2. And we need a 2 pi x, and we want our function here, which is going to be sine of x squared dx. Okay, and so this is what we want to integrate. Well, let's do a little simplification here, or at least rewriting it so we can take the 2 pi out and we get the square root of pi over 2. And in doing this, we're going to need to do a little u substitution. Okay, and so we have this x sine of x squared dx, and we look and say, okay, I'm going to make my u x squared, so that means my du is going to be a 2x dx. And so looking at this integral, well, if I take this 2x dx, then I have my du, and I have a sine of u here. So this is really pi times the integral of sine of u du. Now, I can either choose to evaluate my bounds right now and exchange those, or I can switch back, and I'm just going to go ahead and evaluate because it's nice and easy. So when x is 0, u is going to be 0 squared, which is still 0. And when x is the square root of pi over 2, u is that squared, so that's just going to be to pi over 2. So in doing this integral here, we know the integral of sine is a negative cosine of u, and we're going to evaluate that from 0 to pi over 2. Okay, so we have that negative pi times a quantity. Well, what's cosine of pi over 2? Well, cosine of pi over 2 is 0, and then cosine of 0 is 1. So I'm going to get a negative 1 in there and multiply. That gives me an area of pi. So we look back here, we know we're using the formula 2 pi x times the function dx, and we're integrating that along our bounds a to b. So let's say we have another figure, and it's one that is readily available to write in terms of y. So we have this curve right here that is written as x equals y squared plus 2. And we have this right here of y equals 2, and we also have y equals 0, the x-axis. And we want to revolve this around the x-axis. Now, we could split this up, and we could use disk and washer method, but the difference here would be we got to do 2 different regions, which is okay. It's doable. We can do that. But it's a lot easier to integrate with respect to y because it's only one function here from 0 to 2. So if we revolve this, we get this shape with kind of a parabolic hole there. And we look at, well, let's use the cylindrical shell method here to integrate. And so we look at, well, once again, we want to have 2 pi, and I'm going to have a y times my function of y dy. And the reason I have a function of y is because we're given here our function x as a function of y. So that is my f of y there, the y squared plus 2. And so I'm going to integrate that from a to b, and we'll talk about what a and b are in a second. But I have this 2 pi times the integral of y times that quantity, y squared plus 2 dy. Now, looking at my bounds of integration, I can go all the way back to the original that we want to go to this line y equals. So I know I'm going from 0 to y equals 2 for my limits of integration. So this integral is pretty simple. We get 0 to 2, distribute this y through, and we get y cubed plus 2y dy. Integrate all that, we get a 2 pi times the quantity of y to the 4th over 4 plus y squared, and we're going to evaluate that from 0 to 2. Well, plug in 0, we get 0. Plug in 2, we end up getting 16 over 4, which is 4 plus 4, so that's 8, and that gives us a 16 pi. There we go. So we can do this with other examples if we wanted to look at a hole in a cylinder here. Just looking at some arbitrary radius big R, and we're going to cut out a little r there. Looking at these little shells, we can do that as well. But what I want to show you here is a nice summary of how we can do this. So skipping ahead to these summaries here, in both the disc and washer and shell method, we can apply either of them to almost any situation. However, there is a particular method that is going to be easier in each situation. It all depends on what you're given. Okay, so we want to try to avoid the extra algebra that's needed to solve for functions of x and solve for functions of y. So these two slides here give us a nice summary of the situations in which we want to use disc and washer, or the situations in which we want to use the shell method. So the first, if we are integrating with respect to x, so that means that we're given a function of x and a function of x. All right? And so it's easy to leave it like that, or we just don't want to solve for a function y, or maybe it's not even possible to solve for a function of y. So if we're integrating with respect to x and we're rotating about the x-axis or any horizontal axis, so we can say that this works for any horizontal axis as well. So say something like y equals k, any horizontal line, we want to use disc and washer method. Because we're already in a function of x, we're rotating about a horizontal axis, we're creating these discs and washers. However, if we have this same situation where we have functions of x, but we want to rotate about a vertical axis, so the y-axis or x equals some value k, then we want to use the shell method because it's set up to give us these parallel shells. Okay? Now, when we integrate with respect to y, it just flips. So if we integrate with respect to y and we rotate about the y-axis, then we want to use disc and washer. All right, and this also works for any x equals k. So say we wanted to rotate about x equals -5. If we were going to rotate about that, well then still we want to use disc and washer method if we're given functions of y. But if we're given functions of y and we want to rotate around the x-axis, then we want to use the shell method. And this works for any other horizontal axis in which we rotate. So these two slides here are a great summary and a great tool to use to figure out which method do I want, which method is going to be the best for me.